Welcome to Module 13 of the Six Sigma Institute's Lean Six Sigma Certification Curriculum, which follows both the Council for Six Sigma Certification and the International Association for Six Sigma Certification Bodies of Knowledge. A full copy of the Council for Six Sigma Certification's Book of Knowledge can be downloaded from the course description section for free. In this module, we will be discussing the measure phase of the DMAC methodology. This module will take you approximately 90 minutes to complete. At the end of this module, there will be a 5-question quiz on the topics discussed, which you can complete on your own at any time. You will also find several Six Sigma tools that you can download, including a data collection plan template, a Gage R&R template, and a run chart template, all of which are Excel files. The failure modes and effect analysis is a tool that can be applied by a Six Sigma team in any phase from define to analyze. In this section, we will be discussing the creation and scoring of a failure modes and effect analysis. Often, teams begin working with them in the measure phase because it helps them to identify risk priorities for various inputs and errors within a process. If used properly, the failure modes and effect analysis uses systematic data and team input to set the stage for root cause analysis in the next DMAC phase. Remember, while tollgates do occur and teams move through 5 phases during a DMAC project, hard borders don't always exist between phases. Teams might begin working on measure phase tasks before they even leave the define phase, and it's almost certain that teams will begin some analysis while still collecting data. Ultimately, a failure modes and effect analysis tool should be used when teams need more detailed information about inputs and possible associated fail points than tools that we have discussed previously. It offers some of the information that is also offered in a SIPOC diagram, but it also provides evaluations of inputs. Teams typically create a failure modes and effect analysis in a spreadsheet program, as some calculations are required during the process. To create a failure modes and effect analysis, open Excel and add headers to the first 12 columns, which will be labeled as the process step, potential failure effect, the severity or SEV, potential cause of failure, the occurrence or OCC, the current monitor or control, the detection or DET, the risk priority number or RPM, recommended changes or actions, an assignment of who will do what and when, as well as what action was completed. Later, you will be adding more columns to this chart as you revisit and recalculate the risk priority number after implementation of the changes. Now, we need to score each of the failure modes using a scale from 1 to 10, where a severity score of 1 denotes low risk to the end customer, a detection of 1 denotes a process that will likely catch a failure, and an occurrence of 1 denotes that it happens rarely. On the other end of the spectrum, a severity of 10 denotes a high risk to the customer. A detection of 10 means that the process will not likely catch a failure, and an occurrence of 10 means that it happens all the time. In the chart, we can see a breakdown of how to score the severity, detection, and occurrence based on how likely it happens. The risk priority number is an assessment of risk assigned to a process. In the previous step, we scored the severity, occurrence, and detection risks for a failure mode. And now we need to calculate the risk priority number by multiplying the 3 scores for each failure mode together. By the end of the project, and after implementation of the improvements, this number should be decreased, so we will have to recalculate it later. When we scored the failure modes in the previous step, we used a scale of 1 to 10, but we can also use a scale of 1 through 3, with 1 denoting a low risk and 3 denoting a high risk. If we are comparing many failure modes together, we need a higher resolution, which is why we generally use a scale of 1 through 10 rather than only 1 through 3. Creating a baseline metric for a process begins in the define phase, but teams cannot leave the measure phase without a strong understanding of current process performance. So, in this section, we are going to discuss the collection of data. Because we need to define a process specific metric if possible, and to do that, we need to gather historical data regarding that metric so we have something to compare future data against. This allows us to prove that improvements were made to the process. Ideally, the team should have access to historical metrics for the process. In some cases, the team will have to collect that data from scratch. We will be very busy in the measure phase collecting data so it can be analyzed later. So this will be a long section and one of the longest modules in this training program. We have a lot of information to cover, so get comfortable, be prepared to take some notes, and if needed, watch the video for this module to make sure you didn't miss anything. Before creating and displaying a baseline metric via graphical representation, you have to understand the type of data you are dealing with. Data is either qualitative or quantitative, meaning it either describes something or is represented by a number, either measured or counted. In Six Sigma, teams collect data either as a population sample or a process sample. How teams collect data and the type of data collected determines how the data can be viewed graphically and analyzed. With discrete numbers, we are talking about things that we count, and they are only represented by whole numbers. But with continuous numbers, we are talking about things that we can measure, and that means we can represent any point between two whole numbers. Since it is harder to work with discrete numbers, we tend to turn them into continuous data by converting them into a percentage of the whole. Discrete data is categorical in nature. It is also referred to as qualitative data or attribute data. Discrete data falls into three categories: ordinal, nominal, and binary, or attribute. Some data collected can be expressed in one or more of the discrete categories. For example, student test scores can be conveyed in the ordinal fashion via the grades A, B, C, D, and F, or in a binary fashion via the pass-fail distinction. Discrete data can be displayed via Pareto charts, pie charts, and bar charts. In some instances, the data can be converted to run and control charts using variation within the data or ratios as the item is being charted. Continuous data is quantitative data and is measured in units. For example, the time of day is measured in hours. Temperature is measured in degrees. And almost anything can be converted to continuous data by making it a percentage. Continuous data is visualized in graphs such as histograms and box plots. Box plots were discussed previously, and histograms will be covered in depth when we talk about statistics. Continuous data can also be viewed in the form of run and control charts. Sometimes, a process or activity can be measured in both discrete or continuous data. Depending on the purpose of the measurements, teams might need to pick between the two data types. For example, if a Six Sigma team has identified room temperature as an input into the quality of a product, they will want to monitor the temperature of the room. They can do so by recording the temperature in degrees every 10 minutes. That data would be continuous. Alternatively, the team might want to create a tick sheet, having someone make a mark every hour to note whether the temperature was in the 40s, 50s, 60s, 70s, or 80s with regards to the Fahrenheit scale. That data would be discrete. In this particular example, most teams would choose to record the continuous data. Exact temperature measurements every 10 minutes provide a lot more information than whether the temperature of the room was in the 70s at the turn of the hour. When possible, teams should convert measurements into continuous data. Data can be classified at four basic levels: nominal, ordinal, interval, and ratio. Attribute or binary data is actually a limited form of nominal data. The lowest form of data is nominal, as it exists mainly to categorize and label variables. After that, we have ordinal, which allows us to rank categories in order. Then we have interval data that consists of known or equal intervals, but does not have a true or meaningful zero. Only ratio data has a true 0 point, which is why it is the highest level of data that can be collected and is the form of data that we should strive to use in a Six Sigma initiative. Nominal data is considered to be the lowest data classification level and simply involves applying number labels to a qualitative description. So statistical analysis programs and tests can be applied to the data. The numbers assigned to each category do not provide any information about whether the data is better or worse than other data in the list. In nominal data, numbers don't reflect a scale. For nominal data, central tendencies are calculated not with means or medians, but with mode. The mode is the number that appears most in the set. Statistically, analysis is very limited with regards to nominal data, but some tests can be performed with statistical analysis software. Ordinal data is considered to be a higher form of data than nominal, though it still uses numbers and categories to identify data elements. With ordinal data, though, the numbers themselves actually provide some meaning. The numbers used in the failure mode analysis scales are ordinal data. The numbers are qualitative in nature, but they are also ranked. Central tendencies with ordinal data are measured by either the mode or the median, and common uses for this type of data include ranking various things against each other or rating a specific thing such as a movie or pain level. Ordinal data can be arranged in an order that makes sense, such as a scale of 1 through 10. While ordinal data comes with a logical order, the intervals between the numbers don't mean anything. Interval data is an even higher form of data classification. Interval data provides numerical values that can be arranged in a logical order with meaning. The big difference between ordinal and interval data is that the difference between each interval value provides meaning. If Frank is keeping track of the temperature in his house and sees that at 8 a.m. it was 76 degrees and at 9 a.m. it was 80 degrees, he not only knows that 9 a.m. was hotter, he knows that it was 4 degrees hotter at 9 a.m. than at 8 a.m. Interval data is continuous or quantitative and offers more flexibility when it comes to statistical analysis. Ratio data is considered to be the highest of the data classifications. Ratio data has an absolute 0 point, can be both discrete or continuous in nature, and provides the highest capabilities for statistical analysis in most cases. Some samples of information that can be recorded using ratio data include force, defects per million opportunities, voltage, height, units per hour, and volume. In Six Sigma, we love to use ratio data because it is the most accurate and easiest form of data to work with, and it allows us to conduct analysis and hypothesis testing without having to convert the values to any other form. Measurement system analysis applies scientific principles to help teams analyze how much variation a system of measurement brings to a process. The purpose of the measurement system analysis is to identify errors of accuracy within data collection tools. Teams can then redress measurement systems to create more accurate data captures, or, if that isn't possible, take the possibility of errors into account when performing analysis on data. During measurement system analysis, teams should review multiple components of possible measurement error. Six Sigma teams should analyze whether bias occurs in the accuracy of measurements and whether the measurement has the proper resolution. They need to know what measurement scale linearity exists, whether measurement activities are stable over time, and whether measurements are repeatable and reproducible. Depending on the measurements the team is dealing with, the measurement system analysis can be time consuming and is often why the measure phase of a DMAC project is one of the longest. Teams define the difference between the most accurate measurement possible and the data being collected by the current system. The goal of a measurement system is accuracy, coming as close as possible to the defined target, if not exact. Teams can ensure accuracy of data by verifying that the gauge used to collect data is performing accurately by comparing them against known measurement tools such as verified rulers and scales. Note that accuracy reflects the performance of the measurement tool and not the operator. Whether the employee uses the measurement tool correctly or records the amount correctly is considered a concern of precision. Once a Six Sigma team is confident that a measurement tool is properly calibrated, they can instruct employees or others who are responsible for recording data. Data should be accepted as it is collected for most efficient access and because early review can turn up specific problems with data collection. When possible, teams should not round data but collect data as it is recorded. Measuring at the correct resolution ensures that a measurement system can detect change in the data or process appropriately. A good rule of thumb to follow for resolution is known as the 10 bucket rule. Break your measurement resolution into a tenth of what is required. If the product must measure within a range of 5 millimeters in order to perform, then the measuring tool should measure to a half of a millimeter or 1/10 of that 5 millimeters. Resolution is usually one of the easiest things to correct within a measuring system, but it isn't always cost effective or plausible to measure at the most detailed resolutions. Teams should consider resource requirements when developing a measurement system. If, however, the most detailed resolution is possible, measurements obtained will provide more information about the process and a larger sample size from which to work with. Linearity describes how a measurement system performs across a range. A standard metric ruler in the hands of most people is fairly accurate at measuring centimeters, but is less accurate at measuring millimeters or kilometers. A scale with a range between 0 and 10 kilograms might measure less accurately at either end of the spectrum range. Taking measurements at various ranges with an existing measurement system and comparing those measurements to data gathered with tools known to be accurate across all ranges can help teams find errors of linearity. In some cases, teams can develop mathematical equations to account for the discrepancies. If mathematical adjustments are not possible, then teams should not use the measurement system to measure ranges where linearity errors regularly occur. Stability describes the consistency of measurements over time. If operators are measuring in the same way and using the same tools, and those tools don't have any other problems described above, then measurements should reflect stability on a control chart. We will cover control charts in more details when we discuss statistical process control. Now, if the variation of measurements as reflected on a control chart do not indicate stability, then teams might want to first rule out a problem with the measurement system before determining that the process is out of control. Gage R&R tools are used to ensure repeatability and reproducibility with regards to measurement systems. In most cases, Gage R&R tools apply to measurement systems that involve human operators and appraisers. Six Sigma teams apply Gage R&R tests in order to find weaknesses within such measurement systems. In Gage R&R testing, repeatability means that a single employee using the same measurement system and appraising the same things can repeat his or her measurements. Reproducibility means that multiple employees using the same measurement system and appraising the same things can come up with the same measurements that match or are very close to matching. Most Gage R&R tests fall into two types, attribute and variable. The premise for testing each type of measurement is the same, though the criteria and statistical analysis following the test differ slightly. An attribute gauge R&R is used when Six Sigma teams are analyzing measurement systems for go, no-go data. For example, if operators review an item in the product line and decide simply to pass or fail it, this would be an attribute measurement. An employee might simply be tasked with recording whether the temperature was in an appropriate range, a yes or no measurement. As previously stated, attribute measurements provide the least information about a process. So, in the case of a freezer temperature, it is better to record the actual temperature. Whether that recording was within an appropriate range can be determined systematically from the temperature data. The attribute gauge R&R requires two operators, and all of the samples should be labeled anonymously so that the operators can measure each sample twice without knowing which ones they are remeasuring. Not all data is attribute data, which is why teams can also perform variable gauge R&R tests. While the raw data from a variable gauge R&R test can provide a Six Sigma team with a picture of whether a measurement system is obviously failing or not, statistical analysis is usually required to make a true determination about the performance of a measurement system. This is because with variable measurements, some differences between measurements and operators are likely, particularly when measuring to a very small or large figures, or capturing data in a moving measurement. The variable gauge R&R requires two or more operators and anywhere from 5 to 10 anonymously labeled samples, so that each operator can remeasure the samples randomly 3 to 5 times each. This allows us to calculate the variations between the measurements more accurately. Once teams are sure the best possible measurement tools are in place, they can begin collecting data to be used in the analyze phase of the DMAC project. The most accurate conclusions come when a team can analyze data for the entire population, but that is rarely possible due to time and cost constraints. If you can gain access to automated data or data warehouses, you might be able to collect population data or extremely large sample sizes that better approximate population data. Otherwise, Six Sigma teams must randomly sample the population that is available and use those samples in order to draw conclusions about the population as a whole. To ensure samples can be used to draw statistical conclusions, they must be handled correctly and be the appropriate size. Let's look at the types of sampling strategies that Six Sigma teams might use and why. Simple random sampling works when there is an equal chance that any item within the population will be chosen. For example, if you put 20 marbles of the exact size, weight, and texture in a bag and blindly select one, each marble in the bag has a 1 in 20 chance of being selected. If the marbles are different sizes or weights, those differing attributes can impact the chance that each marble will be selected. Heavier marbles might sort to the bottom of the bag. Bigger marbles might be more likely to be picked up. Therefore, random sampling for statistical analysis requires that the sample will represent similar attributes and percentages as the entire population. The population is n items large. The sample size is n items large. How big the sample needs to be statistically represent the population is decided by a number of factors. Stratified sampling occurs when the population as a whole is divided or can be divided into subgroups with differing attributes. For example, if a shipping company wants to test the accuracy of its estimated shipping times against actual shipping times, it might assume that the results will vary according to the distance a package has to travel. By randomly selecting samples from the entire population, there is a chance that the company might end up with only samples for packages being delivered within a 200-mile radius. To prevent bias in the data, the shipping company might divide the population into 4 subgroups that cover ranges of less than 200 miles, a 201 to 400-mile radius, and a 401 to 600 mile radius, as well as a 600 or more mile radius. By sampling randomly from the stratified subgroups, the team ensures a sample size with less bias. Sequential sampling involves selecting every X item for inclusion in the sampling. Sequential sampling can be used when teams are collecting data at intervals such as time. The team might collect data every 10 minutes. Sequential sampling can also be used to sample physical items. Every fifth item on a product line might be reviewed. Given the right parameters and enough time, sequential sampling can provide valid statistical results. Teams must be cognizant, however, that the sequence of sampling could, in rare cases, skew results. It is possible, for example, that something occurs during every fifth iteration of a process that causes a difference to occur. Non-random sampling should not be used when dealing with statistical analysis because it is more likely to introduce user or sampling error. While all sampling comes with some form of error, random sampling errors can be calculated and accounted for in analysis. The same cannot be said of non-random samples. Non-random sampling includes convenience or judgment sampling. Convenience sampling occurs when a team takes the most convenient measurements. We want to know about the process right now, so let's review the next dozen items that come off the line. That type of analysis only truly tells the team how the process performed at the exact moment in time. Judgment sampling occurs when an expert or knowledgeable person is tasked with selecting appropriate samples. A supervisor might say to his or her team members, select some of your work that represents the normal way you function in a given day. In most cases, the team members selected what they believe is better quality work, thereby skewing any results from the sample. One of the major deliverables coming out of the define and measure phases is the baseline metric. How is the process performing now? And what measurement will the team use to compare the current performance to post-improvement performance? Baseline metrics are numbers, but most teams find that presenting the metric graphically resonates best with business resources and executives. Visual representations also provide teams with a quick way to determine if progress is occurring. The type of visual representation you use depends on whether your major metric is discrete or continuous. Discrete data can be displayed on Pareto charts, and continuous data can be displayed via run charts. You can also use variations or other calculations to convert discrete data to continuous data for display in run charts and control charts. A run chart can be used to monitor the performance of any variable or process over time. With a single, intuitive chart, Six Sigma teams can display trends, shifts, and cycles within a process. They can also monitor a process for concerns, though run charts are not as effective at this as the very similar control chart is. A basic run chart is simply a line plot of data over time, which means anyone can create this type of chart. Most Six Sigma run charts also include a line representing the median of all your data points for visual reference. Depending on the type of information being charted, you may need to convert data to a ratio for a more accurate run chart. For example, if you are plotting the temperature of a surface over time, there is no need to convert data. But if you are plotting the number of patients readmitted to a hospital within 30 days of being discharged, then it helps to convert the data to a percentage of the number of patients discharged within that same period. Statistical analysis software, including Minitab and Excel SPC, creates all of the elements of a run chart automatically from enter data. But at $1,600 per license, most people aren't willing to fork over the cash in order to use Minitab, especially since anyone can use basic Excel functions to create a run chart if needed. It just takes a few extra steps to create, so let's walk through the process together. We start by first creating a data table for a single attribute. Since we will use the example from the book, that attribute will be the number of returns per month. We enter the data labels in the first column, column A, then the single attribute measurements in the second column, column B. Lastly, we add the total number of items you are comparing in the third column, column C. Now we need to add a fourth column, column D, where we will calculate the percentage of the first column of data. In this case, since we are comparing the number of returns to the number of sales, we want to divide the returns from the sales for each period in order to define the rate of return for each month. Now we can stop right here and create a chart from this data only, and it will work just fine. So we need to decide whether we want to create the run chart showing the percentages or to create it illustrating the rate per 100 or per 1000. We already have the percentages, so we could just move on and create the chart. But these percentages may end up being too confusing. So you may actually want to illustrate a rate per 100. To do this, we would add a fifth column, column E, where we would multiply the values from the rate of return column by 100. Now we have a number that is easier to present to management and other company employees. Next, we need to calculate the median of the numbers we plan to chart. And we do this by using the median formula. Choose a cell off to the right of your data table, one that won't be accidentally highlighted, and type in the equal sign, the word median, and the open and close parentheses. Now you can select returns per 100 data point column and click enter to generate the median for the dataset. Once we have our median, we highlight just the data label column and the figures to be charted, in this case, the returns per 100 column. With those two columns of data highlighted, we go up to the ribbon and select the Insert tab, then choose Charts and select Line Chart. This will automatically create a line chart using the data you highlighted. It will generally automatically format the table based on the previous settings or based on the template that you are using. So we can go ahead and choose the Table Format tab from the ribbon and select any one of the pre-made formats that are available, or even create your own using the formatting options. While we calculated the median, we did not select it, and as such, a median line was not automatically created for us. So now we need to manually create that line from the number you calculated earlier. Go ahead and select the Insert tab from the ribbon, choose Shape, and select the Draw Line option. This will allow you to draw a line freehanded. With the line tool selected, we need to manually draw a line where the median should be, horizontally across the chart. If we were using Minitab, then this line would have been created automatically. But at more than $1,600 per license, I find that the few extra steps to draw the lines by hand are worth it. Don't forget to adjust the color, thickness, and type of line that you want using the formatting tools built into Excel. By the time the measure phase is complete, the team should have agreed upon the key measurements and come up with a baseline measurement of the process performance, analyzed the measurement systems and identified any issues that might contribute to analysis errors, corrected the measurement system to remove error risks, calculated process variation and sigma level, conducted an appropriate sampling to allow for statistically valid conclusions, and the sponsor or champion should have signed off on all of those elements. The team and its sponsor should have come to an agreement on key measurements. In the BPO industry, the service level agreement usually outlines the metrics used to measure service level. In a Six Sigma initiative, it is our responsibility to define these. These will become crucial after we implement the improvement and seek to control the process, as we can use these metrics to define remedies or penalties when they are not met. The key performance indicators are specific to the process. They are part of, and in the BPO industry, they are what ensures that the service level agreement is being met. In Six Sigma, we use these KPIs to monitor and control the process because the data can be statistically analyzed. By the end of the measurement phase, before we collect the data, we need to ensure that the data is accurate. And we can only do this by first analyzing the measurement system for variations. We do this to ensure that the measurements are always accurate and precise. We have to determine that the measurements are repeatable and reproducible, and that the data is linear and stable. More importantly, we have identified any potential points of bias and eliminated them from the measurement system when at all possible. In the event that we found any issues or errors with the measurement system, we corrected them. We have ensured that we are using the correct gauge, that we took into consideration the 10 bucket rule. Where possible, we removed any human interaction from the measurement system in order to reduce bias, and switched the system over to a digital one when the budget allows. When it does not allow, we have developed mathematical equations to adjust the measurements where needed and replace the measurement system when adjustments are not possible. While most of the calculations will be dealt with in the analyze phase, there are some things that need to be determined by the end of the measurement phase. We will need to calculate the process variation and sigma level in preparation for the analyze phase. We also have come to understand the customer's concept of a defect, so we can determine the metrics needed to define success. We have calculated the process variation and dispersion, so we know where and what our focus should be on. We should already know what the defects per million opportunities are and the defects per unit are, because these would have been discovered and calculated as we calibrated the measurement systems. The measurement phase is where we collect the data needed for the analyze phase. So in order to complete this phase, we need to have already conducted a large enough sampling that will allow us to draw valid conclusions about the population. If you have access to the entire population data, then you would be better off using it rather than using a sample, because the greater the representation of the population, the more conclusive assumptions can be about that population. But since collecting data from the entire population is expensive and time consuming, we generally need to conduct a sampling. You should have already agreed on a sampling method, determined how much room for error is acceptable, and compiled this data for the analyze phase. Before you can begin the analyze phase, you need to finish the measurement phase, and that requires an approval from leadership. That means you will need to have the project champion or sponsor sign off. You will have to present the status of the project to the sponsor or champion, which means the data must be compiled and reviewed for any issues. The measurement data must be within specification that the sponsor and team agreed upon, and if there are any issues, they will need to be rectified before the champion or sponsor can sign off, and of course before you can begin officially working on the analysis of the data.